In this unit, we're going to look at the structure and reactivity of alkynes, which contain a carbon-carbon triple bond. And without belaboring the point too much, the main focus here is going to be on the analogies between alkynes and alkenes. Many reactions of alkynes are highly analogous to reactions of alkenes that we've already seen. So we're going to make a lot of those analogies to, again, efficiently assimilate information about alkynes that we need to know. There are a couple unique aspects to alkynes, particularly terminal alkynes with the triple bond on the end of the chain. These are relatively acidic in an important way, and this allows us to deprotonate them and use them as nucleophiles in SN2 reactions, which is going to prove highly valuable synthetically, as we'll see. So we're going to describe and apply the structural properties of alkynes as we've done with other functional groups. We're going to look at that acidity of terminal alkyne CH protons and apply their conjugate bases, acetylide anions, in reactions. We're going to predict the products of reactions of alkynes, drawing many analogies to alkenes, and we're going to apply these reactions in multi-step synthesis. Alkynes contain a carbon-carbon triple bond. Each carbon in the triple bond is sp hybridized, nothing too fancy there. And like alkenes, the pi electrons in alkynes are fairly Lewis basic. Terminal alkynes are particularly unique in their reactivity because they contain sp-CH bonds, which we don't see really in any other functional group other than the alkyne. This terminal CH bond is relatively acidic, and we can see this experimentally in pKa values. We've got a pKa of 25 for acetylene. The analogous alkene ethylene has a pKa that's almost 20 pKa units higher, 20 orders of magnitude less acidic than acetylene, and ethane, the saturated analog, is even less acidic. So it's relatively easy to deprotonate acetylene and related terminal alkynes where we have an R group here instead of H. This deprotonation generates an anion called an acetylide. And typical bases used to do this, we need a pKa greater than 30, right, to ensure complete deprotonation of the terminal alkyne proton. NH2 minus and something like sodium amide, NaNH2, and sodium hydride, NaH, are commonly used for these deprotonations. And both of these bases deprotonate alkynes completely, terminal alkynes, to produce acetylide anions. And these acetylide anions are great nucleophiles. At the same time, they're not horribly unstable. The reason these terminal alkynes are relatively acidic is that there's quite a bit of S character associated with the sp hybrid orbital that lone pair, that new lone pair in the conjugate base, is sitting in. That high S character stabilizes the electrons, brings them closer to the nucleus, and makes the acetylide anion relatively stable as carbanions go. At the same time, this is still a great nucleophile, and we can apply it in SN2 reactions. We'll see that a little bit later in this unit. The way we make alkynes is via elimination, 99 times out of 100. But the trick to make alkynes is that we need two leaving groups in the starting material to establish the two new pi bonds in going from an alkyl dihalide to an alkyne, which contains two pi bonds. So here, for example, we've got two sets of HBr that both are eliminated in the presence of a strong base to produce the carbon-carbon triple bond. This can get a little tricky, right? If there were H's within these R groups, beta hydrogens over here, for example, over here next to the two bromines, we could end up with isomeric alkynes in general. And this we generally want to avoid. And so we have to be a little bit careful, especially when we're working with these so-called geminal dihalides, these 1,1 dihalides. Vicinal dihalides, 1,2 dihalides, will eliminate selectively to give an alkyne between the two carbons that are bearing the halogen atoms, since our two sets of HBRs in this case are definitively between these two carbons, right? So vicinal dihalides, which we know how to generate from alkenes using halogenation reactions, eliminate selectively to give these alkynes. Now, when we're making a terminal alkyne via these elimination reactions, for example, starting with a substrate like this, something interesting happens because the terminal alkyne is quite acidic. It's actually more acidic enough to be deprotonated by the NH2 minus used to accomplish this elimination. So quite frequently, we go through an acetylide anion in these reactions that is protonated by water, typically added on workup, to give the neutral terminal alkyne. And in all of these reactions, this second H2O step is designed to use up any excess base we might have and neutralize the alkyne if necessary when we're generating a terminal alkyne, as in this case. Here we're just applying our understanding of how to make alkynes via elimination of dihalides. And here we have a geminal dihalide, 2 bromines connected to a common carbon. And one thing to note here is that we don't have this issue of inequivalent beta hydrogens because there are no hydrogens linked to this tert-butyl carbon right here. It's quaternary. So there's only one carbon from which we could eliminate H, and it's this methyl carbon. And notice we've got 2 sets of HBRs here, the blue set and the red set, both of which can be eliminated provided we use excess base, excess NH2- to eliminate off all of that HBr between the methyl group and the carbon bearing the 2 bromines. So an E2 elimination is the name of the game here. NH2- is the base and deprotonates at the beta carbon. Br- is eliminated at the same time, and we go right to this alkene. This is a classic standard E2. The difference now, though, is that this alkene retains a hydrogen and a bromine that can be eliminated in a subsequent E2 elimination type of step to generate a triple bond, converting the alkene into an alkyne with elimination of another equivalent of HBr. In this case, though, notice we've generated a terminal alkyne. There's an H left on this carbon at the end of the chain involved in the triple bond. And there's NH2- still around because we're using excess NH2 under these reaction conditions. So that will deprotonate the terminal alkyne right here to generate an acetylide anion. And to recover the neutral alkyne, we actually need to treat with water. And so while we end up back at the same terminal alkyne that we generated here, it's important to keep in mind that the base is going to deprotonate this under the reaction conditions in step 1. We need to add the water if we want to recover the neutral alkyne. If we didn't add the water, then we would potentially wash away or lose or generate as a sodium acetylide salt our alkyne when what we want is the neutral organic compound, not an ionic compound.